You did,
I saw that.
well, you were doing traces in your homework.
Well, you didn't tell
We've
us.
been doing a little bit of.
The last two.
Okay, so clearly asking you to do a trace was too tall of an order, even though you did traces in your homework.
I'm only 5'4", you can't do that.
Okay. All right, I will make a future. Okay, so are there any outstanding questions before we launch into the material for today? None? Okay. All right. So we today is going to get a little ugly, but it's going to be a necessity because I think I promised. It's my turn, guys. I think I promised you that we were going to have to revisit some ideas with which you thought you were comfortable. In particular, the ideas of vectors and related quantities, and we're going to have to really formally sort of redevelop them so that we can generalize them to more complicated scenarios like curved spaces. So I talked a little bit about vectors at the end of the last lecture and made several comments that are all going to become important as we go forward, but the one that was most important for today is that one way to think about vectors is that they have components. When you set up a coordinate system, the vectors have components which transform in a certain way. And so what we're going to spend our time today doing is discerning what way vector components should transform. And in that, we're going to encounter some important technology. Okay, so we have to start somewhere. We have to start with something with which we know a little bit about. And so what we're going to think about is the displacement vector ds, which many people would write with a vector sign over it. Indeed, in Physics 1, we would smack people if they left off the vector sign. But we don't need vector signs in this class because you're all so sophisticated that you know that ds is a vector. And the many things we know about ds is that this thing is, as a vector, it's invariant. But when expressed in a coordinate system, it gets components that do transform. And what's nice about the ds vector is that its components are just coordinate differentials. Okay? So this is literally just like if you do a delta x vector, and then your vector looks like this. Or actually, maybe this is delta r vector. Maybe that's the way people like to do it. Okay, but the important observation is that the components of a displacement vector are themselves just coordinate differentials. Okay? Now, why is that important, you ask? Well, everything is sort of predicated on the idea that we're changing coordinates, we're transforming coordinates. But if the components of this vector are just coordinate differentials, the components of this vector must transform like the coordinates. Because they, after all, are just little segments of coordinates. Okay? And we know how coordinates transform. Escaped. We know. Oh man. This is a first for me, I won't lie. We know how coordinates transform. Sorry, I'm going to try and keep this going. If we do a coordinate transformation, then we can transform our coordinates with some linear operator that we can express like this. Okay, where this is, as we talked a little bit about last time with the index notation, this is a transformation matrix from the unprimed frame to the primed frame. And you can always represent transformation matrices as matrices. All right, you can always represent a transformation by a matrix operation. And as a consequence of this, if we want to ask how the differentials transform, well, they just transform in exactly the same way. Okay, so the upshot of starting with the displacement vector is that we already know how its components transform. Now what we would like to do is we would like to figure out how the components of an arbitrary vector transform. And if you were to guess, you might say, well, they probably transform the same way. Why not? But we need to actually back that up. And in backing that up, we'll develop things a little more formally, but it's also going to give us a segue into something that's a little more abstract. So pay close attention to the following strategy, because I am going to repeat the following strategy several times. I'm going to do it today for vectors, and then I'm going to do it at the end of today's lecture for a different kind of object, and then we'll do it for more general tensors in the next lecture. So this same story is going to play out several times. Okay. So the trick to generalizing this beyond this one vector is to remember that the ds itself is invariant. Okay. And to remember what ds really is. Okay. So ds is secretly a set of components. But just like I wrote earlier for the normal case of 3 dimensions, each component is multiplied by a basis vector. Okay, we're used to using I hat, j hat, k hat for x, y, and z, but we don't have to use those basis vectors. And so I'm going to give our basis vectors what's going to seem like a pretty terse labeling. E hat sub mu in parentheses. Okay. So the hat just indicates that I'm going to use normalized basis vectors. We don't have to use normalized basis vectors, and there are cases in this class where we won't, and I'll show you later on how you switch back and forth between them. Putting the mu in the subscript is a little weird, or sorry, putting the mu in parentheses is a little weird, but all that's telling you, and this is something I find that, especially when you're new to index notation, this is a hard pill to swallow, but I promise. The thing is that here the mu is labeling the components of the vector, okay? But here mu is actually labeling which of the basis vectors you're dealing with, okay? So for example, in the more familiar scenario, and I'll just do this in 2 dimensions for brevity. Remember, I hat itself is a vector, and j hat is a vector. So I hat has components. It has x component and y component, and j hat has an x component and a y component. But this label here is not telling me which component of the I hat vector I want to deal with. It's telling me I want to use the I hat vector. So we put that in parentheses here to remind us it's naming the vector we're using, not a component of a vector. These, on the other hand, are true components of a vector. Okay? But, with the rules of index notation, there's a repeated index. Doesn't matter that this was in parentheses. So implicit in this is the idea that we will do what to this sum? Let me see what my first card is. Oh, it's Sarah Jones. Surprise.
Sum over them?
Yeah, we sum over them. Okay. So secretly that would be dx0, e0 plus dx1, e1, etc., etc. Okay. And now here we go. Here's the, and just to give you an idea. Do you have a question? Yeah.
The superscript on the dx, is that a mu or an m?
It's a mu. It's a mu. I will very rarely write m's until we get to relativistic dynamics, where we talk about mass. So until then, everything is going to be in mu. Okay, so just to kind of give you a picture of what this looks like, if we set up an x, or if we set up a coordinate system with an x1 and an x2 axis, remember everything we're doing now is going to be predicated on we've defined a coordinate system. We've actually coordinatized the space with space-time. Then what we've done is we've created basis vectors that point along the coordinate axes. This is what's called a coordinate-adapted basis. In principle, you do not have to do this. You do not have to set up basis vectors that are parallel to your coordinate axes. It's not necessary. Things get really ugly if you don't, but that's a freedom you can use in certain contexts. Okay, so here's the flow of the argument. It goes like this. ds is invariant, so what that means is that when I transform ds, and in this class, arrow means I'm doing a transformation, this becomes a ds prime, which would be dx mu prime e hat, and I'm going to prime the mu index there. Okay? But since ds is invariant, when I do the transformation for ds, I should actually get back an equivalent expression. So ds prime should be the same as ds. Okay? Now, those of you who are sort of in tune with this kind of argument can already see what I'm going to do. But I'll save the punchline for the end, and so what I'm going to do is some formal manipulations, but in the end you'll go, oh yeah, that totally makes sense. I could have expected that from the beginning. But here we go. So first of all, let's fill in what we know. We know how dx mu transforms. So I'm literally just going to replace dx mu prime by the expression that we're familiar with. So this is going to be lambda mu prime nu dx nu. I'm just going to follow my notes because no, we'll do this as a mu. We haven't got a mu anywhere right now. Okay, and then I have e hat mu prime. Okay, and now what I'm going to do is I'm simply going to guess a form of the transformation of the basis vector. I'm just going to guess. All right, and I'm going to make an inspired guess basically based on how the indices are set up. So I got a mu prime lower, and I want to turn it into just a mu, or some low index that's not primed. So what I can do is I can add in a transformation with the lower mu prime, and then some upper index like that. And then let me just write this and see. So what this thing would do, even if I don't know what it is it would sum on the nu, so the nu would go away, and I would be left with a mu prime, which is what I have here. Okay, so that's just kind of an inspired guess based on what the indices are doing. All right? Now this, of course, is some new object.
What does WTF stand for?
Well, what do you think it stands for?
What's that for?
What's that formula? Exactly. What's that formula? So let me shuffle my cards. Let me carefully and thoroughly shuffle my cards. All right. So now this is a symbol, like it's got a lambda, it's got prime and unprime indices, and some of you in homework help last night know, or homework help, this is not this one. Some of you last night I kind of explained what this, gave you a preview of what this is. But right now this is an unknown thing. This thing we know is the transformation of the coordinates from the original coordinates to some new set of coordinates, okay? But if we take this expression, and remember with index notation you can move things around at will, we can write this as follows. Okay? But at the end of the day, we want this to be equal to dx mu e hat mu. We want it to be equal to the thing we started with. So I'll draw a card to get someone who will walk me through the following, or the rest of the argument. And, oh, it just turns out that Sarah Jones is on top. And that's fine.
Okay.
I did shuffle them. So Sarah,
Yeah.
I would like for this expression to become this expression. What must then be true?
The two lambdas have to be inverses of each other?
The two lambdas have to combine to give me a delta function on mu and mu. Okay? Because I need something which is going to turn that mu index into a mu. Because here this is mu and mu, right? And we all know, I mean, well, I say that. I hope you all know that, most of you know that the delta function, the Kronecker delta function here, this is just an object which says this is 1 when these two things take the same value, and it's 0 when these two things take different values. Okay. So this is a way of forcing the value of mu to be equal to nu somewhere else in the expression. Okay? But as Sarah rightfully pointed out, this is really just the statement that if this is lambda inverse. Because really this is just sort of matrix code for something times something else is equal to the identity. Because if you wrote this thing as a matrix, it would actually be the identity. Okay? Now, there was a lot of discussion in help last night, but I want to go ahead and kind of clear up some confusion. When I go from lambda to lambda inverse, I want you to notice that the left stays left and the right stays right. The only thing that changes, oh wait a minute, hold on, something is weird. Oh no, the new primes or something, that's fine. Left stays left, right stays right. All that happens is the prime moves from an upper to a lower term, okay? We could ask, what is this quantity? All right, and for those of you who discussed this with me last night, what is this equal to?
Transpose.
That's the transpose of lambda. Because remember, the leftness and the rightness of the indices is telling me row, column. It's always left is row, right is column. And if you are swapping the left and the right, keeping everything that's up, up, and everything that's down, down, and primed where they stay, then you're just transposing. Last but not least, what would this be?
The transpose. Inverse transpose.
Exactly. This would be the inverse transposed. Okay.
Which is not the transpose inverse.
You can do it either way. You can do it either way. So there you have now seen all four places you could put your indices, okay? You could put it this way, or this way and this way, and primes in all possible locations. Hands across America. You guys can duke it out for who goes first.
Go. Yeah, so I'm just confused on what happens if you put them in a row. So you have like mu prime, either all on the bottom or all on the top.
You won't. With lambdas, you'll never do that.
Okay, but for like matrices.
For matrices, okay, so for matrices, we can actually, okay, so first of all, for matrices, well, okay, so to use a word, which we will learn next time, but applies to all of those things that you were manipulating last night without knowing it, for tensors, you will not have a primed and an unprimed index. They will either all be primed or they'll all be unprimed, okay? Then for a tensor, say G, mu, nu, if you want to transpose it, you would do this. Okay? And then since there's no primes to worry about, you don't really have any place. So the reason there are four combinations here is because I'm moving primes around in addition to swapping things left and right. Now we will today talk about if you have this, then can you somehow raise an index? But we're going to talk about that later. Here you do not do that. Here there's literally four versions of a lambda. And lambdas are very special in this class. They are transformations. Okay? They're the only things we encounter that have a primed and an unprimed index. And we're going to talk about these other things in due time. Okay? Yeah.
So those E hats are your basis. That's your basis.
They are your set of basis vectors.
Okay, and so we can say that a set of basis transforms by lambda inverse.
Yeah. So that's exactly what I'm about to summarize.
Okay.
So good. So in summary, what the shit is that? I'm not going to be one of those assholes that like take broken things and stick them in my. Oh man. Wait, how many points do I get for that? So in summary, okay, so in summary, this is what we have for vectors, or for the infinitesimal displacement vector. We have that this guy, and I'm going to do this little summary up here, transforms into this form. Which is the expression for ds prime, but since it's invariant, that should give us back ds, and that is true if we have the following: the components transform in the usual way, and the basis vectors transform according to this new rule. where, of course, what we have in mind here is that lambda mu, mu prime, lambda mu prime equals delta mu. Okay, so I'm going to put that in a box because that set of observations is going to be sort of a bedrock for much of what we're about to do. Okay. We good?
Something about that. Are you missing something in the E term?
In the what term?
In the basis vector transformation term? There's only a single lambda there.
Yeah, there should be.
In the
Okay.
last line, you have it different down there than you do up there.
Yeah, why is there a
The mu prime is in the bottom.
Oh, you guys are so bothered.
Well, I
Well, you did completely flip it.
This is a
You are.
foreign language, we're trying to learn the grammar.
Okay, that's fine, that's fine.
You just gotta
So one at a time, well, I'm gonna take, no, these are all good questions, so one at a time. The first question was, why is there only one lambda here? Okay, let me go back to the argument here. I start with this, and I transform first just this one with a lambda. Then I transform this with one lambda. But I take these two lambdas, and I argue they have to combine to the identity. Okay, so each thing only transforms with one lambda. On to the next point, and this is where you will eventually get, I promise. I wrote over there that this is true if lambda mu prime mu, lambda mu mu prime is equal to delta mu mu. Okay, so, and again, this is just the curse of being comfortable with this. First of all, the identity is symmetric, so you could always write this like this. You can transpose it, it won't matter. And these you can always move around. Okay. And then if I just happily say, well, I'm going to change the label for nu and mu, I'm just going to call this mu and call this nu, and I'm fine doing that as long as I do it on the other side, then we've got the expression I wrote up there. So it's the same expression, okay? At the end of the day, where you'll get, though, is that when you want to write down an expression like this, really all you got to pay attention to is that the indices match up. So when I wrote this down, I just started putting in indices, and I said the prime has to go away, so let's make sure one is up and one is down, or one is up and one is down. And then the indices of what I have left over have to match the indices the right-hand side. It all works out that way, actually. Adria.
So then is E mu equal to E nu? 'Cause that's what you said, like you said, dx mu E nu is equal to dx mu E mu? Or is this one of those, no, I'm gonna, do you see what I'm trying to-
So what? Okay. So what I have here, yeah. So yeah. Good question. So in this expression, I could have called this mu, but I didn't want to because now you have mu in 4 places, and that's kind of a no-no because that's two. You would sum them all together, which you don't want to do. So I'm actually giving them separate labels here. Okay, but in this expression, since there's only one mu, I can just use a mu again over here. I mean, this would be, yeah. So to make you more comfortable, I could have written this. And that would have lined up a bit more with the choosing the new here. But normally when we write these transformations, we just stick with one letter. But the important thing is in this derivation, when I made this step of writing down how this E transforms, I consciously chose not to make this a mu, because you might have then be tempted to sum that mu with these mu's, and that would have given you the incorrect expression. This index is different from this index. Here, though, they don't, only one of them appears, so I can call anything I want. Other questions? Okay. So what we've done is we have figured out the transformation rules for a single vector, a coordinate displacement vector. What we would like is a set of transformation rules that apply to an arbitrary vector. But here is the cool trick. And you'll understand why I went through this formalism. For an arbitrary vector, V, okay, I'm not going to put a vector sign over it, it's just a vector V. Okay, this is going to have components that look like that. But the components of an arbitrary vector are not coordinate differentials. Okay, so we can't just assume that these things behave like coordinate differentials. We studied this vector because its components were coordinate differentials and we know how coordinates transform. For an arbitrary vector, these are not coordinate quantities. They're components of a vector, you know. But when you expand the vector into components, you expand it in the same set of basis vectors. Right? I mean, when we write down a vector in dimensions, God, I always want to write S. You know, if it's a coordinate vector, we do this. But if it's a velocity vector, we do this. So we use the same I hat and j hat, even though the components are different. Okay? And now here's the payoff. Are you ready? I'm going to say it in words and then just write the result up. Are you ready? We know how these transform. That's what we just figured out. But here's the cool part. We know how these transform, and we know that this thing has to be invariant. So we can basically play the exact same argument that we did before, except this time we start out knowing how these transform, and we use the invariance to figure out how these transform. Where in the first case, we started knowing how these transform, and we used this invariant to figure out how these transform. Okay? Does that make sense? You need two pieces of information. You need to know how something transforms, and then you need to know that the whole thing is invariant. In the first case, we knew how the components transformed, and then we used that to figure out how the basis transformed. Now that we know how the basis transforms, we can come to an arbitrary vector and use the invariance to figure out how the components transform. But of course, what's the answer?
Same way.
They transform exactly the same way as they do here. Okay, so it's what you would have guessed, but you've proved it formally. Okay, so what we have now is the transformation rule for an arbitrary vector. Oh, yeah, I don't know.
Yeah.
Do this. Yeah, I'm gonna do it. Oh, it's awesome! V mu goes to V prime.
Where
Mu prime, which is V prime, which is V, because it's invariant. If
Leo.
V mu prime is this, V mu, bam, there it is. No pause, just throw money. Just throw money. Yeah, okay. So what we have is the transformation law for vectors. I felt that.
You got a whole penny for that.
Okay, so now like you might be sitting there asking yourself, why are we spending so much time talking about vectors? Okay, well, the first rule of this is that knowing how vectors transform is almost half of knowing everything you need to know about tensors. We'll talk about the other half in a minute. Okay? But the second reason, which is going to be an argument that plays out when we talk about more complicated things like tensors, is the following. We are going to have to, at some point, take three-dimensional vectors, like velocity, and generalize them to four-dimensional vectors in space-time, something called a four-velocity. But the thing is you've got to make sure that the object you're building is actually a vector in space-time. And if you want to figure out whether it's a vector in space-time, you just check, does it have the right transformation properties? Okay. And we'll see when we start trying to build vectors in 4 dimensions that the naive thing we might write down actually won't transform correctly. And then we'll have to do something a little bit more sophisticated. So we really have to have a set of rules for how we identify a vector. And then this same thing will generalize to more complicated things later on. Now, in the notes, and I'm not going to do this now, but if you look at the notes when I post them tonight, there is a very completely 100% explicit example of this transformation with all the indices and the basis vectors in a very concrete scenario where you literally have a vector in a 2-dimensional coordinate system, and then you rotate the coordinate system like this. And this is something very concrete. We can write down the matrices. We can do everything explicitly. I do it for you in the notes, and it uses all of this notation. So if this is new and confusing to you, I strongly recommend you take the time to look through that example in the notes, but I'm not going to go over it right now. Okay? And if you don't understand it from the notes, you're welcome to come to my office hours and we can go over the details. Okay? All right, so what I want to do now is I want to take the second important step in this story that will get us set up so that next time we can talk about tensors. And I want to introduce a new object called a dual vector. Okay. Now what's interesting, and this better be a good year.
Oh, nice, you found a penny.
Yeah. Well, I mean,
What year is it?
holy snap, it's 2018.
Wow, that's a rare one, I'm sure. It's like an antique.
You know, when I was your age,
anymore.
when I was your age, I worked at a coin and stamp collection shop.
The
And so I used to know all the stuff that was valuable, and I've forgotten it all. But the one thing I did learn was anything you have that you think is valuable probably ain't.
That's the spirit.
I know, it was terrible. It's like, if I hang on to this penny until I'm 100, it'll be valuable. No, it'd just be an old penny. Nobody will care. All right, okay, so dual vectors. So again, this is going to be a very important part of the story of tensors. In fact, it's the second half of the story, so you want to pay attention. These are things which, believe it or not, you have worked with before, even though in your working with them before, no one probably named them as such. But we can define dual vectors by basically three conditions. And it's going to start out very similar to what we did to define or talk about vectors. So dual vectors are straight, directed objects in the same way that vectors are like straight directed objects, defined at a point in space or space-time. Okay? So remember what we talked about with vectors? We said that you cannot think of a vector as something that extends from one point to another. You literally have to think of the vector as being defined at a point. And then it extends in what space? Let me pick a card from the deck. Oh, it's Sarah Jones.
Cool.
I gotta shuffle these. Sarah.
I'm gonna end up.
Sarah, in what direction do the dual? In what direction do the vectors point?
Is it the magnitude of the, no, I actually don't know.
Mike.
I'm sorry.
Space that's like tangent to the actual space.
Exactly, in the
Oh.
tangent space. So the idea we have is that if you have a spherical surface, and I want to think about a vector here, what I do is I construct a flat space which is tangent to the circle, and we call that the tangent space at that point. But the tangent spaces are different for different points. The tangent space down here would be something tangent to that point. And this is one of the things that's going to make our life more complicated in this class, is the fact that the tangent spaces are different at different points. Okay? Now, we don't want to confuse dual vectors with vectors. And so, We don't want our dual vectors to live in tangent space, because that's the space that vectors live in. We got to have them live in a different space, so I'll draw a random card and see who's. Oh, it's Sarah Jones. Sarah.
all Sarah Jones.
If I had my way today.
Show us some
So what
examples.
space? So what space do you think dual vectors might live in?
On tangents.
There's so much whispering right now. Whisper space.
I don't know, whatever is analogous to tangent space, but with dual vector.
So tangent.
Is it gonna be like some three-dimensional version of tangent space? I really don't know.
So, well, you're actually not far off. So I heard. So first of all, let me point something out. So, just to be very clear, the surface of the sphere is two-dimensional.
Yeah.
The surface of the is two-dimensional. So you'll notice that the tangent space itself is also two-dimensional. Okay, and that's good because if we have a vector on this surface, we expect it to have two components, and that's good because the tangent space has two components. Now I heard somebody whisper maybe these live in normal space, but the normal space to a sphere is a one-dimensional space. And so if something lives in the normal space, it will only have one component, which is an important space to consider, but it's not the space where these live. These are going to have as many components as vectors. So without any further ado, these live in cotangent space. Okay. And the term cotangent might seem weird, but it actually has a lot to do with the fact that, in a sense, combining a vector and a dual vector gives you a number. In some sense, it's predicated on the idea of combining a certain vector and a certain dual vector to give you the number 1, which is exactly what we get when we combine tangent and cotangent of an angle, right? Because they're inverses. Okay. So to continue, dual vectors are invariant objects, just like vectors are. So the whole sort of line of reasoning we used talking about vectors, saying they themselves do not change under coordinates changes, is true for dual vectors, but they have components which transform in a specific way. Okay? So there's a lot of similarity to what we said for vectors, and of course a lot of the arguments we made for vectors we're going to make for dual vectors. Okay? But so far we don't have any connection between dual vectors and vectors. There's similarities, but we have no like point of connection. The third condition is where we get our point of connection. Dual vectors linearly eat vectors and poop scalars.
Incredible.
Okay, so what I mean by that is the following. Okay? Oh, don't be children. Somebody says the word, you just lose it. Okay, so here's the deal. So I'm going to write this symbol omega. That's going to be a dual vector. Okay? And then I'm going to show you what the eating of a vector looks like. And I'm going to show you in an example that also expresses the linearity of the eating. Okay? So first of all, I'm going to take a linear combination of vectors. Okay? In this expression, V and W are vectors, and then A and B are just scalars. Okay, so this is a linear combination of vectors. Now, the idea that the dual vector linearly eats these is just the statement that I can split that up into the separate eating of AV and then BW. And then the idea that it poops scalars is just the idea that at the end of this operation, you should get a scalar. Okay? So So there is a mathematical equation embodying the idea that dual vectors linearly eat vectors and poop scalars.
What do you think eating?
Huh?
What do you think eating and pooping means?
Okay, we're gonna get some formalism. Hold on, we're gonna develop some formalism for what more specifically that means. But I want to ask you a question to kind of lead off, and that is, if I'm talking about vectors as objects which are invariant under coordinate changes, and I'm also talking about dual vectors as objects which are invariant under coordinate changes, okay, then what the hell is a scalar? Because how do you normally define a scalar?
Variant under coordinate changes?
Yeah, you think of a scalar as something which is invariant under coordinate changes. So this is where, like, the language that you've been using for a long time, we have to kind of go back and rethink. Because I'm claiming that both vectors and dual vectors are invariant under coordinate changes. And I argued to you that that should be the case. Like, if I'm driving my car south, that fact doesn't change no matter how you pick your x and y coordinates. Yeah.
Does it come down to a difference of description where you say dual vectors are straight directed objects and then scalars are not?
Well, actually, you started along the right track and then you kind of went in a different place. That's tied into it, but it has to do with the description. And that is, when we coordinatize the space, vectors and dual vectors get components which transform. Okay? But those transformations are offset by the transformations of the basis. However, if we coordinatize a space and we do a coordinate transformation, our mathematical expression for a scalar doesn't care. Like, scalars don't have components. They don't get decomposed. Okay. So even though everything is truly invariant, our description of vectors and dual vectors involve things which transform. Our description of scalars don't. Okay. All right. Okay, so now we are going to blaze through an argument that's very, very similar to what we did for vectors. Okay, I'm going to use slightly different symbols. So let's start by coordinatizing the space. And then I'm going to introduce a set of coordinate-adapted dual basis vectors. Okay, so what we have in mind now is that where for vectors we used e hat mu, for dual vectors our basis is going to be theta hat with an upper index. Okay? Now, when we did our argument for vectors, remember we had this crutch to start with because we looked at this one particular vector, the ds vector, and we knew something about that. We knew how its components transform. And then from that flowed all this other love, and we eventually got to this general transformation rule. We don't have an intuitive starting point for dual vectors. We don't really know what they are. Okay? So we're going to need some nugget to start with, and I argued that it's going to come out of this condition 3. So let's actually write a mathematical version of what condition 3 is. So condition 3, mathematically, is going to be expressed as follows. If I take a basis dual vector and combine it with a basis vector, then I get delta mu nu. That is going to be a mathematical statement of how the basis dual vectors and the vectors combine to give me numbers or scalars. And of course this is 1 if mu is equal to nu, and it's 0 if mu is different from nu. Okay. Are you ready? Yeah.
So that object that we could say is the identity, you're basically saying that is a scalar.
Yeah. You Ready? Here we go. This is an invariant. It's literally just a number. It's either the number 1 or it's the number 0. Okay? I know how these transform. And I know that I have overall an invariant. So I can use that to figure out how these have to transform. It's the same story we played before. Okay? But of course, what's the answer going to be? If these transform one way, how do these transform? With the inverse. Okay? So having written this down, we can immediately, and I do it in detail in the notes, but we're not going to repeat stuff we've already written before. So at the end of the day, what we find is that our basis dual vectors transform with a transformation matrix that is the inverse of the transformation matrix that we use to transform the vector basis. Okay. And again, I fill in the details of the argument in the notes, so if you want to see all the steps, they're there. Yeah.
Does that imply that there's something similar between the dual basis vectors and vectors, and then the vectors because they transform in the same way? Is there some connection between those two?
Yeah.
They transform in. So, are you asking me, is there a connection between the dual basis, the dual basis vectors and the components of a vector?
Yeah.
Because these transform actually like the components of a vector.
Oh, okay, yeah.
And the answer is they do transform in the same way, but they're entirely different objects. Remember, these are components.
Yeah.
But these are actual objects. These actually themselves have components and point in a direction. Yeah.
So is there any way to visualize cotangent space?
I'm going to give you a homework problem. So the idea. So really, another way to think about it is that cotangent space is what we generally call the dual to tangent space. Now you might not have. You've probably seen dual spaces before, but they might not have been named as much. Has anybody ever heard of the notion of reciprocal space in condensed matter? Okay, you're going to have a homework problem where you actually construct a concrete dual space for a space which is actually a lattice, and then you will create the dual lattice, and it will be created in exactly the same way as we're defining the cotangent space in this case. So it's not, I'm going to give you in a few minutes a connection between this weird abstraction to something you've been using for a long, long time. But there's a certain sense in which I want to come back to this idea that the reason we call this cotangent space is if we start out with tangent space for vectors, cotangent space for dual vectors is sort of built on this idea that the basis for cotangent space transforms in exactly the opposite or inverse way for the basis in tangent space.
So it's not exactly like a cotangent function or
Right.
like the,
Well, it smacks of the idea that cotangent is the inverse of tangent in terms of multiplicative inverse. Okay, so just to have somebody answer the questions. Oh, it's Sarah Jones. Sarah, there's one part of the story that is so far missing. I know how vector components transform. I know how basis vectors transform. I know how dual basis vectors transform. What do I need to figure out in order to complete the story?
Dual basis component transfer? Maybe? Or like...
Components of dual vectors,
Yeah,
I think
there
is
we
what
go.
you mean, yes. We need to figure out how components of dual vectors transform, okay? So a dual vector, I can write as a set of components, and let me see what I'm going to label it. Yeah. Expanded in the basis of dual vectors. And I'm not even going to touch the card. Sarah,
Yeah.
where do you think I should put the index on the components of a dual vector?
These ones should probably go, actually, do you want them up top? Or do you want them opposite of the basis dual vectors?
The latter.
Okay, opposite, so on the bottom.
Yeah. Okay. Now, are you ready? Talk about getting a lot for your money. Talk about getting a lot for your money. Are you ready?
Okay.
Check this out. You ready? This is a dual vector. It's invariant. We know how these transform. So we can figure out how these transform. And the answer is not surprising at all. The components of a dual vector transform according to that rule, which you will notice is exactly how basis vectors transform.
Are you ready for a good one?
Yeah. What is that, like gold? Oh, it is gold. Is that like a gold dollar? Oh, no, it's New Zealand. Oh.
Ah, that's what you
Even more valuable. Hold it for 100 years.
Okay. It'd be rich if you.
64 cents.
Nobody
One
knows that
more.
exists.
Yeah, they have.
I might be going to New Zealand this summer, so that.
Oh, yeah.
Get the Australian government.
Okay. All right, so in the end, there are 4 transformation rules that we have obtained. And I'm not going to summarize them again. There's everything for the story of vectors. We know how the components transform, and we know how the basis vectors transform. And then we have, for dual vectors, how the components transform and how the basis transforms. And in all of these expressions, the lambdas that I'm talking about, they're the same lambdas. So this is lambda inverse, this is lambda, and this is lambda inverse. Okay? Now what's really cool about it is we went through all of this fancy sort of gymnastics to get these rules, but at the end of the day, all you really need to pay attention to is whether the index is up or down. And then you can immediately write down the transformation rule. I don't even really need to tell you what you're working with. Because if you have a lower index and you do a transformation, well, all you do is you write down the lambda that takes this index and gives you back a lower mu prime. And that's what that will do.
I thought they had to be like that to do stuff together.
Say it again?
Like, I thought I would have guessed the mu prime would have been on the left and the bottom, and the mu would have been on the right and the top. Because don't they have to be that?
So this mu is summed with this mu. So these mu's in principle disappear from the right, and I'm left with a mu prime, which is what's on the left.
Okay.
That's an equal sign. The left and the right have to have these same indices. This is the thing I'm starting with, and I'm transforming it. So with the arrow, I'm literally going from the unprimed to the prime. And then this is an equality. I'm writing the new thing in terms of the old thing using a transformation matrix.
Well, then if the mu prime's on the left on the other equation, why is it on the right?
Mu leaves me with a mu prime, which is a mu prime there. That's the same index structure. And then here, the mu and the mu sum and leave me with a mu prime up here, which is a mu prime there. This is the same spirit of what I've written in all of these transformation rules. Yes?
Sure.
Do you disagree?
Well, I just thought that it had to be on the right side if you were summing it with something that would, no, it's okay. I'll figure it out.
Well, I mean,
If you think of them like those two objects,
Yeah.
them being
Oh.
they commute, so you can just move that to the left, and then you can have the low and the upper that you want to see, right?
Is that what you want to see? Is you want to see it like this?
Yeah, that makes me more comfortable.
Okay, sorry. Yeah, and you're totally legit in writing it that way because you can move these. I usually write it like this because I think of this as acting on this. That's why I write it to the left. But in evaluating it, you can write it any order you want, and that's fine. Okay? This is the order you would write it if you wanted to use what? Matrices. But with index notation, we don't have to write it in any particular order because we don't have to use matrices. Okay, so we got dual vectors on the table. Now I'm going to connect this to something that you've all seen before. Because when I make claims like you've worked with dual vectors before, I want to back that up. And also just to sort of illustrate how we're really taking things you've seen before and we're just giving them a sort of a more formal definition. So, yeah, okay, so we have now a completely explicit way of writing down what it means for a vector to eat, a dual vector to eat a vector, okay? So if we wrote this out in full gory detail, it would look like this. Okay? Where we can move things around because we're using index notation. This is just expanding the dual vector in a basis. This is expanding the vector in a basis. But if we move things around, then we have this. But we said that this is going to give us the delta function on mu and nu, which is going to take one of these and make it equal to the other one. So at the end of the day, this is going to become this. And then using the summation convention, you have something like that. Okay. Now, interesting observation. This looks kind of like a dot product, right? It looks like the dot product. But technically, it's not the dot product. The dot product is an operation combining two of what kind of objects?
Vectors.
Two vectors. This is the combination of a vector and a dual vector. Clearly, there has to be some connection to the dot product. Okay? So what do we mean when we say the dot product? Well, what we mean is essentially that the dot product is an operation that takes two vectors and forms this particular combination. Where this particular combination is, of course, a scalar. But the question is, okay, this W is the same as this W. How do we formally do this? So how do I start with a vector V and then somehow, through some magic of this operation we call the dot product, turn this vector into a dual vector so that this combination gives us back the kind of expression we're used to? So transposing it works in a certain situation, but we have to be a little bit more sophisticated. So transposing works in the context you're familiar with, but we're going to have to do something a little more formal. Who said transpose? You did, okay, yeah. You got a question?
It's take the like the Hermitian of it. Look at the vectors Hermitian. No, what's it called? The adjoint.
Inverse transpose.
Yeah.
That's the Hermitian.
So,
That's the conjugate.
yeah, so you're all going in exactly the right direction. So let me just very quickly write this up here. So let's go back to the dot product that you've seen before, okay? So if I take two vectors with components Vi and Wj, you know that the dot product between those does this. V1, W1 plus V2, W2 plus dot, 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 okay? So if I want to do this as an operation on things with indices I and j, the way that I can write it is like this. Delta ij v I w j. Okay? Now let's just think about that for a second using what we know about index notation. The i's are repeated, which means I sum over the i's. The j's are repeated, which means I independently sum over the j's. Okay? However, this is the Kronecker delta. And the Kronecker delta says you can do that, but the only non-zero terms are the ones where I is equal to j, which is going to give you exactly this expression. Now, are you all comfortable with me saying that this is represented by this? And here's the trick. What if that was our definition of the lower j? Then this would be consistent, okay? And now here's the very, very important observation. This is essentially the identity. And the context in which we're talking is rotations in, for example, R3. What role does the identity play in the set of transformations corresponding to rotations in R3?
It's the metric.
It's the metric. Good. So when we go to four-dimensional Minkowski space and we're doing special relativity, what we discover is that if we are given a vector and we want to form the dual vector from it, we're just going to apply, sorry, this should be eta, the metric of the space.
Just forcing it in, basically.
Say it again?
You're just basically taking a vector that doesn't particularly belong in that space and then using the metric, just like forcing it in. It's like, all right, now you're there.
Yeah, so the way, one way to define the metric is that the metric is it's actually a multilinear map, but we'll just say linear map. It's a linear map from the space of vectors into the space of dual vectors.
So you couldn't do that if you had a vector that was like three-dimensional, and then if your metric was four-dimensional and you tried to put a three-dimensional vector.
Yeah, that wouldn't work.
Okay.
No.
It would have to still be defined by some vector.
Yeah, everything has to be consistent. So if you're working in 4 dimensions, your metric is a 4x4 thing, and your vectors have 4 components. It always has to be consistent. Yeah, Adrian.
Is there like a trick of sorts to tell if something's a dual vector or vector? Because all these just look like V's and W's.
Sure. Okay, so the first thing I'm going to say is that fortunately, in the future, we are going to be able to almost completely dispense with the basis. Because it turns out that if you just look at the components, you can figure out what everything is supposed to do. All right? The basis always just comes along and takes, it formally takes care of things. So what I mean by that is when I write this, I'm just going to skip straight to this expression. Okay? Now, in that notation, if something has an upper index, it's a vector component. If something has a lower index, it's a dual vector component. And what I have just shown you is the rule for taking vector components and turning them into dual vector components. Now, important question, which Sarah will be glad to tell us. If I wanted to get a vector component from a dual vector component, what do you think I should use?
The inverse of metric?
Exactly. And what should we call that?
Would you put it up top?
Yeah, put the new and the new at the top.
See how just making the indices work out gives you the right answer. So what we discover is that n eta, or eta nu mu, is the inverse of eta lower mu nu. Nu mu. You can say it in the order because it's symmetric. So the metric takes us from vectors to dual vectors, while the inverse metric takes us from dual vectors back to vectors. And you know this is the inverse because if you took a vector to a dual vector and then went back to the vectors, you better end up at the same vector. So these two operations should be inverses. Okay? All right, so that's all we've got for today. The one thing that I want to point out, which people get really, really confused about, and I'm going to say this now, I want you to notice in these expressions, there are no primes. When you use the metric to go from a vector component to a dual vector component, that's all happening in one coordinate system. We're not transforming from coordinates, one coordinate system to another. We're literally going from vectors to dual vectors. Okay? I could do this expression with everything primed. And that would make perfect sense. The lambdas are the only place we are going to see mixed primed and unprimed indices because those are transforming us from one coordinate system to another. All right? Again, there are a few more things written in the notes than I had time to go over today. You really want to become comfortable with this because these two things, vectors and dual vectors, and this notation is going to be our basic starting point for tensors, which we're going to talk about in detail next time. Okay? You're welcome.
That's not your fault. I didn't go to physics X. Yeah. Well, so next time don't come.
Be the end of the recording?
I guess. I wanted to express my sorrow for not being able to attend, but I guess that was more of an invitation.
So the idea is,
It's okay. It's fun. I like it.
we want to take the upper index and get back to the upper index. Because we want to get another vector just in a different coordinate. So just to get the indices to work out, it has to combine with this, which means it has to have a lower one.
I mean, I feel like I was Look, get a load of that dog! What? I only need to get two.
That upper index.
And one of them was something that I literally had no way to answer.
That's why we're using something with two lower indexes. We will encounter.
I said, like,
We're going to encounter objects with many
some
indices.
other
And there'll be
creative
objects
space, or like some three-dimensional version,
upper and lower.
which I think were two good guesses. They were good attempts at a guess. They were
They'll basically have
I was
effects
gonna guess the normal
drained
size.
from the
Well, and
face
some
measures.
people guess
Now it's
So I'm gonna make a Costco run pretty soon. So anything in particular I should get other than just the normal.
I think the normal is great. Yeah, I've heard that people are really satisfied with it.
yeah. So it's weird. All of this can be represented.
Yeah, and
by
they do have good options there. Yeah.
This would be represented by a matrix. Will somebody turn the camera off? Sarah, will you turn the camera off?
Yeah.
Don't break it when you do it.